We're going to start this chapter doing some basic physics, but we'll try to keep it light and as interesting as possible because I think physics is awesome. We're going to start off with speed, velocity, and acceleration. So speed you guys are familiar with. You look at your speedometer in your car and you're going 55 miles per hour. Physicists make a really strong distinction between speed and velocity. Velocity is basically a speed, but you have to specify a direction. 55 miles per hour north, in my example here. Up, down, east, west, towards the galactic center, it needs a direction. Right? So, once you make that distinction, we're going to say an acceleration is any change in your velocity. Any change. Change your speed or change your direction, and that's an acceleration. So, as a physicist, I would say you have 3 accelerators in your car. You have your gas pedal, your accelerator, the one you're used to. You have your brake pedal, which changes your speed. I would call it a negative acceleration. And you have your steering wheel, which can change your velocity by changing your direction. I would call that a tangential acceleration, right? So you've got your gas pedal, your brake pedal, and your steering wheel. They're all accelerators to a physicist. And we link them all together because all 3 of them require a force to do it, require an unbalanced force to speed up, to slow down, or to turn. And in this chapter, we are going to be talking about gravity. That's going to be our main focus, our main force. And gravity can speed up an object, gravity can slow an object down, and gravity can turn an object. So let's look at the free fall of gravity for a second here. Free fall basically means falling without any support or falling without any resistance. So for now, we're going to pretend that there's no air resistance, no drag, no friction. Just pretend it is in free fall. Near the surface of Earth, gravity tries to accelerate all objects down 22 miles per hour each second. So that's the rate of change. Every second, gravity tries to change it by 22 miles per hour. So if you drop an object, which means you're going to let gravity take control of it. If you drop an object and it's allowed to free fall, in 1 second from time of 0, in 1 second it will change by 22 miles per hour. I know up here the units are in meters per second, but I thought you would appreciate also hearing about it in miles per hour, so that way you could put it in context of your everyday life. So after 1 second of falling, it's going 22 miles per hour. Or you could say 10 meters per second. If you go another second, gravity is allowed to make it free fall for another second, it will speed up another 22 miles per hour. So it'd be going 44 miles per hour. Right? In real life, air resistance will start to matter the faster it goes. But in basic physics problems, often we just say, pretend there's no air resistance. How fast is it going when it hits? For each second, you add on 22 miles per hour. Right. So, one thing that your book mentions and goes through a little bit is force and momentum. I'm just going to define a force, so that way when I say the force of gravity, everybody at least knows what we mean by force. And I'm going to define momentum only because we're going to use it a little bit later towards the middle and end of this chapter. So at least that way you've got the definition. Right. A force is a push or a pull. You can push with your hand, you can pull with your hand. Magnetism can push and pull another magnet. Gravity happens to only do the pull. So gravity tries to pull all mass towards all other mass. Momentum is a little bit more abstract. It depends on an object's mass, which we haven't really defined yet. It's coming a little bit later in the book. We'll do that here in a second. An object's mass times its velocity. Not that you'll ever have to calculate it, but that's what it depends on. The more mass something has, the more velocity it has. That can affect its momentum. And after teaching several semesters of conceptual physics, this is the most basic, useful way I have found to define momentum. It's a measure of how difficult it is to stop an object. Okay. How difficult will it be to stop an object? So an object that's already stopped has zero momentum. Let's say you've got two vehicles moving down a highway at 65 miles per hour. One's a fully loaded semi and one is a smart car. Right? Both of them are going the same velocity, highway speeds, but they don't have the same momentum because that semi truck has a whole lot more mass. And if it's got a whole lot more mass, it's going to be a whole lot more difficult to stop. What you do probably need to focus on, though, two things you really need to keep straight, is the difference between mass and weight. So while you can gloss over force and momentum, don't skip over mass and weight, because I will do some homework questions on it and probably also on the test. Mass is going to be the amount of matter in your body. So I have a certain amount of matter in my body. I think last time I converted it something like 80 some kilograms. Right. Kilograms happens to be the international unit for mass. We scientists prefer to use mass because your mass doesn't change depending on where you are. So we usually like to deal with mass. Weight is what Americans tend to deal with in their everyday life, which makes things a bit confusing. And the English unit of weight is pounds. Right? So technically the weight is the force that you apply to the floor. The force that you apply to the floor. Or you can think about that kind of reverse. The force that the floor applies to you. Right? That's weight. Right, so be careful. Pounds is a unit of weight. Kilograms is a unit of mass. You've probably never had to deal with the unit of slugs. How many slugs are in something? That's the English mass unit. The international unit for weight is a Newton, but you should be able to just use pounds. We'll just use pounds when we're talking about it on a test or homework. Weight. Weight can be a little bit tricky. So we've got this little cartoon of a guy in an elevator. Right? He has a certain amount of mass. His mass will not change throughout this whole animation. His mass is constant. But his weight can change based on the situation. So right now his weight in pounds reads 140. He's standing on a scale. The elevator is stationary. He weighs 140 pounds. If you're in an elevator moving at constant velocity, so you're not accelerating, your weight doesn't change. Right? But when you accelerate, your weight can change. So let's say elevator accelerating upward. So he's constantly increasing his speed upwards. So imagine that the floor is having to push into him more strongly to get him to be moving upwards faster. Right? So the scale is pushing up into him harder, and that actually makes him weigh more. Even though his mass hasn't changed, he weighs more. I can do the elevator accelerating downwards, so it's going to be reverse. If you want to speed up going down, the elevator floor will fall out from underneath you, and thus you will not press on the scale as strongly, and you will technically weigh less. You will weigh less. Your mass didn't change, but you weigh less. and elevator in free fall. It's fun when it's at an amusement park and you're supposed to be in free fall. Okay. If the elevator is falling at the same rate you are falling, 22 miles per hour per second, gravity near the surface of Earth is making you free fall. You're just speeding up with gravity. If you're both falling at the same rate, you can't push on the scale. The scale can't support you, because if you accidentally push off of it, you'll actually move up above the scale and no longer be able to touch it. It's not supporting you. You are weightless. So take a second and just internalize that idea, write it down, put a box around it. You can be weightless on Earth. All you have to do is be falling without support, and you are weightless. You are in free fall.
Live from deep within an actual astronomer's head, it's Ask an Astronomy Brain Parasite.
Hi, you're watching Ask an Astronomy Brain Parasite, the show where we tap into an actual scientist's brain to bring you science. Wah wah. Wah wah, what's today's question? Wah wah. Why are astronauts weightless in space? Isn't there gravity up there? Now this is a tricky one. You see, astronauts aren't actually weightless up there. They only appear weightless. And there's a very interesting reason why that might surprise you. Let's break it down. First of all, there is definitely gravity in space. A lot of it. Take the Earth. Its gravity is so powerful, even as far out as the moon, that it holds the moon in orbit so that it can't leave. And the moon is much further from the Earth than the area around the Earth where astronauts appear weightless. And frankly, Earth's gravity is powerful even much further out. Gravity doesn't end, it gets weaker with distance, but it keeps going. At this very moment, the gravity of planet Earth is tugging at stars and planets and distant galaxies. And they are tugging on the Earth right back. That's how powerful and far-reaching gravity is. And everything out there has gravity. The other planets, moons, asteroids, never mind the sun, which is the largest source of gravity in our solar system. So with all this gravity everywhere, why do astronauts appear weightless? When we launch astronauts up into orbit, why don't they fall right back down to Earth, or into the sun for that matter? It's for the same reason that the moon doesn't smash into the Earth, or the Earth doesn't get pulled into the sun along with all the other planets. All of these objects are basically in free fall. And when you're falling, you feel weightless. Think about skydivers. When they're falling, they look a lot like weightless astronauts floating around, don't they? Or better yet, imagine being in an elevator. When an elevator begins moving down, you feel a little lighter. If you're in a fast-moving express elevator, you notice it even more. And if there were no elevator cable, you would feel completely weightless. At that point, pushing off from the ground would cause you to float around like an astronaut, at least until you hit the ceiling or the elevator hit the ground. Astronauts appear weightless because they too are in free fall. If we put an astronaut up above the Earth and released him, he would fall right back down. But let's say we put him up there and gave him a shove sideways. He would still fall towards the Earth, but he'd also move in the direction we shoved him, so he'd end up over here. He'd basically fall in an arc over the surface of the planet. And this is a constant process. Since there's no air resistance in space, he wouldn't slow down. At any given point, he'd still have all of his motion going in one direction, and he'd still be pulled toward the Earth by gravity. So he'd keep falling in a circle around the entire planet over and over. It's a free fall that could keep going for a very long time. This is exactly what's happening everywhere in the universe. And I mean everywhere. Astronauts in orbit are falling around the Earth. The moon is falling around the Earth. The Earth's falling around the sun. The sun and all the other stars in our galaxy are falling around each other in the supermassive black hole at the center of our galaxy. Our galaxy is falling around other galaxies in our local cluster, which in turn, you get the idea. The bottom line is, there's really no place you can go that isn't affected by gravity. Everywhere in the universe, everybody and everything is always falling towards something. And if it doesn't feel like you're falling, it's only because you're standing on something else that is falling. And that is why astronauts appear weightless in space. Thanks for watching. Wah wah, the show's over. Let's shut her down. Wah wah.
NASA's Spitzer Space Telescope is managed by Caltech's Jet Propulsion Laboratory in Pasadena, California. Astronomers do not actually wear white lab coats, except maybe the weird ones. No astronomers were harmed in the making of this video. His brain will be turned back on shortly.
So, I have in the readings that you guys are going to get to skip section 2, just because we need to cut something out. There's too much material. Okay? And we're going to skip up to conservation laws in astronomy. And there's different types of conservation. There's conservation of momentum, and there's conservation of angular momentum. And for the rest of the class, the only one you really need to worry about is conservation of angular momentum. So how about I tell you what angular momentum is? All right, so we did momentum, the idea of how hard is it to stop an object. Well, since we have orbits and rotations out in space, they have their own type of momentum. So angular momentum is basically how difficult is it to stop an object from orbiting or from spinning. Because a spinning object will want to stay spinning. An orbiting object will want to stay orbiting. Okay? So, angular momentum stays constant unless it gives or takes angular momentum from something else. So angular momentum stays constant. So that can be kind of a tricky question on a homework or test. Because if you have Earth orbiting the Sun, sometimes it's going a little bit faster in its orbit, sometimes it's going a little bit slower on its elliptical orbit, but at all of the points, doesn't matter if it's going fast or slow, its angular momentum actually stays the same. Here, let me go back one slide and point that out. Right? If it's going faster, it happens when the radius is smaller, and that keeps the angular momentum the same. The law of conservation of angular momentum, right? Angular momentum is constant unless it gives it or takes it from another object. So let's imagine you have a nebula. That's all by itself in empty space, basically a big cloud of gas. Right? It might have a tiny bit of rotation, just a little bit of rotation. Right? And when it collapses, assuming gravity is strong enough, it's going to collapse the nebula. Gravity is going to pull it tighter and tighter and tighter. Right? It's losing radius. It's losing radius, but it has to find a way to keep its angular momentum constant. So if it's getting smaller, the only way it can compensate is by speeding up its rotation. So in physics, when something loses radius and it's spinning, it'll end up spinning even faster. Okay. This ice skater one, you're going to presume that she's all by herself, not really pushing or pulling on any other objects nearby, but that she is spinning. She's spinning on the ice. Right. Have you ever noticed when you're watching ice skating, figure skating on TV, they pull in their arms and they get going really, 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 really fast? Right? That's the law of conservation of angular momentum. When you pull your arms in closer to your body, that reduces your radius and pulls all of your mass closer to the center. And since you have to keep your angular momentum constant, your speed compensates. You speed up. If you were to bring your arms back out, you would slow back down. It's really weird, but you should try it. Find a spinny chair, something that spins really well. Get a couple of soup cans and hold them out in your hands just so you have a little bit of extra weight, a little bit of extra mass, and get yourself spinning really nice and fast as you can, safely. Right? And then once you're spinning on your chair, bring your hands in, bring that soup really close to your center, and you will speed up and you will feel it in your gut, and it's pretty awesome. You should do it. And once you start feeling a little ill, take your arms back out, move the soup back out to the larger radius, and you will slow back down. Energy is the next topic on our docket. So energy is kind of a vague definition. Energy is usually, the ability to do work, the ability to do something. And there's lots of different types of energy, lots of different ways you can store energy. Right? Your book is going to go through chemical energy, right? Thermal energy, just the energy of the temperature of an object. So gravitational potential energy. First, let me just point out potential means stored. The energy is stored. It has the ability to do something if you let it go, if you let it fall. So if you're holding a ball above the ground, it has the ability to fall if you let it go. So it's stored energy, and once you let it go, that height will decrease, the ball will fall, and it'll pick up speed. Here's the ball over here with some speed. Right? We would call that kinetic energy, the energy of motion. So energy can transform from one type to another. Gravitational potential energy, once you let the ball go, will transform into kinetic energy. Right. When you need energy, you eat food which has chemical potential energy, stored energy, and you can turn it into energy of motion. You can turn it into thermal energy. So energy can be transformed from one type to another. Right? But we say that energy is conserved. Now, a roller coaster is not ideal, it's not perfect. There's friction in the wheels, friction in the bearings. So in the long run, you will eventually lose some of that useful energy to the environment. Some of that energy will be wasted into thermal energy by friction. Nuclear energy is just the idea that energy is stored in the nucleus of an atom. And the nucleus of the atom is all of the protons and neutrons. You can count them all up and figure out what element it is. Right. And if you change the nucleus, so change it from a hydrogen into a helium, or you change it from a carbon into an oxygen, if you change the nucleus itself, if you change the type of atom that it is, you can get energy out. And so most of what we're going to talk about with nuclear energy is going to be fusion in stars. That's how stars make their energy, is by taking smaller elements and fusing them, gluing them into a bigger, heavier element. Or if we're talking about planets, planets have complicated, huge atoms inside of them, like uranium. And uranium is not stable, and uranium can break apart into two smaller elements. And fission can also give you energy. So both of those can give you energy. So E equals mc squared. It's exciting when you can tell somebody you understand it. So let's go through it. E is just the amount of energy that you're going to get from fission or fusion. So we've got the E. Let's do the C next. C squared, which is just C times C. Right? C is just a constant, a number that you look up from a book and you plug it in. It's always the same number. It happens to be the speed of light. So C stands for the speed of light, but it's really just a constant, a number you plug in. The fun thing is the M. The M is mass. So this is the idea that the energy that you're getting from fission or fusion is actually coming from mass. And it's actually going to be the amount of mass difference. So let's say, let me get a pen. Let's say that here you have a scale. There's my scale. Right? And you weigh the uranium beforehand. And let's pretend that it weighs a value of, 300. So the scale reads 300. That must be a lot of uranium. Okay. You let it undergo fission, and you capture everything that uranium turned into. You capture all the little byproducts. And if you capture every little byproduct and you weigh it on a scale, don't you think it should still be 300? If you captured all of the little pieces that come out of that reaction, you would think that it should still weigh 300. It doesn't. I'm making up some numbers here just to give you the point. Maybe it weighs 299.999. A little bit of mass is lost through that reaction. It just disappears, meaning it's not mass anymore. It went to energy. So this took us until like the 1920s to figure out. People were trying to explain how the sun generated its energy, and it wasn't until the 1920s, 1930s that we realized that mass is actually a stored form of energy. Okay. So that little bit of mass lost, 0.001, that is what you would plug in here for M. That's the change of mass, the amount of mass that turned into energy. I think that's awesome. Very cool. So you could do the same thing for fusion. Right? You weigh all of the before products. You weigh them. I don't know, let's say, make up a number if it weighs 2. And you capture everything it turns into, and you weigh everything it turns into. It would be 1 point, I'm just making up some numbers here to get the point across. Maybe 1.9999. Whoops. Yeah. Some of the mass is lost. Some of that mass was changed into energy. Okay. So that's fission and fusion. Changing the nucleus so that way some of the energy, some of the mass can turn into energy.